Thank you. Okay, so I guess I'm supposed to talk about information theoretic view of the communication complexity that we're talking about in this workshop. So I wasn't sure exactly what I should talk about. So what I figured what I'll do is take all the titles of the talks, all this, and then see what the talks are about, and then talk about whatever comes out. Okay, so these are the titles. As you can see, I just took out the times and the names of the speakers and so on. So let's see what we get.
What does this website do?
You'll see in a second, assuming it works. Let's see if I like it. Can you see? Not so well. Okay. Yeah, okay, I think I like it. So I think, what do we have here? I think we have information complexity. I think that's one clear topic that we have in this workshop. I think we have interactive communication. It's another clear topic. And I think we have amortized communication. If you want, we can run it again. Maybe it will look even better. But I think we can see 3 topics coming out. So we have information complexity. They came out here. Right? And interactive communication and amortized communication, I think is pretty good. So maybe we can talk about these 3 topics. So that's what this website does. Okay. And if you want to know how I thought about this, I got this idea from Ted Cruz. So I can tell you later how. Okay, so, all right, let's see. Okay, so, all right, okay, so we're going to talk about these 3 topics. Interactive communication, amortized communication, and information complexity. And we'll get an information perspective of these topics. And I think now looking at the sizes that things came up, then maybe interactive communication should be first, and information complexity second, and amortized communication was a little smaller, so let's keep it last. All right. Okay. So first, interactive communication. So there were lots of talks about interactive communication, and I won't tell you about the information theory version of interactive communication. That's what it's called, and it's been there for many years. Okay. So how come? Right. Okay, so talking about that, and all right. So first, let's very briefly talk about what we're going to do. So we know that when a sender conveys information to a receiver, one-way communication suffices. If I have something to tell you, then I can just talk to you. Like on the TV, they just talk to you, and that's sufficient. They want to tell you the news. They don't need any feedback from you. Okay? However, if the receiver has related information, then interaction can help. Okay? And so what we want to do now is want to explore that. And unlike the interactive communication that we heard about this week, in this interactive communication, there are no transmission errors. So everything I say, you hear precisely. Everything you say, I hear precisely. Okay? So what we're going to do is we're going to look at some examples. We'll see the role of interaction. As always, we'll look at the number of bits that you need to achieve a goal, and get some theoretical bounds and some open problems. And of course, this will be highly compressed because I have 30 minutes for 3 talks, so it's not very much time. So here is the first example. So, and I should say that unlike the results that we have heard, most of the talks we have heard this week are brand new. These talks are very old. Like this is like maybe 20 years old. And some of them we'll see maybe somewhat old, but also maybe somewhat new, as we'll see. So, okay. So imagine, so the N teams in the NBA and 2 teams play in the game. And typically the results are announced over the radio. They said there was a match between the Celtics and the Lakers and was won by the Lakers. I don't even know if these teams still exist. So, okay. So now, so this is what a typical announcement would say. Now imagine that one day you hold your radio and you hear that there was a match between the Celtics and the Lakers. And then I grab your radio and I hear that it was won by the Lakers. So as a result, you know the 2 teams that played. You know that the Celtics played the Lakers, but you don't know who won. I know who won. I know that the Lakers won, but I don't know who they played against. Okay. And now you want to know who the winner is. Why? Because this was your radio, and I stole it. So you want to know who the winner is. So you want to know who the winner is, which of these 2 teams, and I don't need to know who they played against. Okay. So is that clear? So information just needs to go from me to you. So the question is, how many bits you must transmit? You can ask on the average or at worst, and here we'll talk about the worst case. Okay. So basically, the situation is this: you know 2 teams that played. I know one of them, and you want to know which one I have.
This is what's called indexing in R. One person has number I, another one has bit string, and one number I has bit string.
Okay. So the only thing I would say is this: that I don't know the index. So it's not that I know that I have the first or the second. You know Celtics and Lakers. I know one of them. I don't know if it's the first team or the second team. All right. So here, so there's an informant and recipient, like like everything in this talk. I'm the informant. I want to tell you something you want to hear. I know the winner. You know the game. I don't need to know anything. You want to know the winner. Right. So the question is how many bits we need to communicate in the worst case. And so first, let's look at one message, because I don't need to know anything. I can just transmit to you. Okay?
What do you mean you don't want to know who won the game?
I know the winner.
Oh.
I don't need to know who lost.
Oh, you don't want to know?
No. I actually don't know. I don't want to know any of these things. But it's just for the...
Why did you steal the radio?
I thought there was something that was going to talk about debates or something. So, okay. So, L1, 1 will stand for the single message. So L1 is the number of bits you need in the worst case. Okay. And so clearly L1 is less than log n, because we can order the n teams, and I can just tell you who won without using the fact that you know a lot of information. So L1 is less than log n. The question is whether we can do any better. Okay. If we had 1 more minute, then I would have let you answer it. But since we are really pressed with time, I'll just let you know. So if you have any one-way protocol, like in this case, we're looking at L1, the winner determines my message, because all I know is who won. So what I transmit is a function of the winner. Okay. So here are the teams, there are n of them, and here's what I transmit. Imagine that there are 2 teams, in this case, the Lakers and the Pistons, for which I transmit the same message. Imagine that this is my protocol. This is bad, because if they happen to play each other, I'll transmit 0 and 1 in both cases. You cannot transmit back, so you will not know who won. Okay, so therefore, if we have a one-way protocol, we want it to be correct, every team has to have a different message. It has to be the case. And therefore, you have, if 2 teams have the same message, then there's an error if these 2 teams play. So all messages must be distinct, so must be n different messages. So at least one of them will have a length log n. So therefore, if we insist on a single message, on one-way communication, we need to transmit log n bits. Okay. So the question, of course, is whether interaction can help. And notice that I don't need to learn anything. I only want to transmit to you. So it's not clear that you should be transmitting to me. So that's the question. Can you tell? So 2 messages. You transmit first. Remember, you know the 2 teams. And then I reply. So how can we do it? Again, with 1 minute, you would have solved it. But with 0 minutes, I'll tell you. So we order the teams from 0 to n minus 1. And these are the binary representation. you know, so these are location 1 up to 4 in this case, 1 up to log n. You know 2 teams that played, right? So what you're going to do is you're going to tell me the teams that played. So you know the 2 teams that played, they have different binary representation. There must be a location where they differ. So you tell me the location where they differ, and then I tell you in that location the winner has something. So for example, in our case, you know the Lakers and the Celtics. There are 2 different sequences. They must be different in at least 1 location. In this case, they actually differ in 2. You choose the first one, location 2, and tell me the two teams differ in location 2. And I tell you, I know that the Lakers won, so I know that they have won. So I tell you they have won in that location, and that's sufficient for you to distinguish. Okay, so how many bits did we, so it works, and how many bits did we use? You transmitted one of the coordinates, the n teams, so there are log n coordinates. To describe one of them is log n. And then I respond with 1 bit. Okay? So we saw that with 2 messages, we went from log n to log n, logarithmic. Okay. Another interesting thing is that even though you didn't want to tell me anything, you actually transmitted essentially all the bits. Okay. So the question is, can we do better? Can we go beyond that, either with 2 messages, with any number of messages? So this is a special case of a general problem. What is the general problem? There are 2 communicators, we call them informant px and py, and each of them has a random input, x and y, and both know the underlying distribution. Okay? They use an agreed upon protocol, and you allow them to exchange m messages, or rounds if you want. And LM is the number of bits that both must transmit it in the worst case. So we're counting bits going in both ways. We're not cheating. And we're looking at the worst case. So L1 is the number of bits you need with a single message, L2 with 2 messages, and so forth. Clearly, these numbers are non-increasing because you can just have empty messages. Okay. So the minimum is going to be they're all non-negative, so there's going to be some minimum. We call it L infinity. And this number, because we're looking at the worst case, we will not care about the distribution, except what we'll care about is the support set. Because the probabilities don't matter, just what is possible and what is not. Because we're looking at the worst case. Okay, so it's determined by the support set, which are the set of all x and y's that have positive probability. Are we okay so far? So fast forwarding to the results, what can you say? What can you say about this? So you can show that the maximum improvement that you can achieve by interaction is at most logarithmic. So with 1 message you need L1. With any number of messages, you need at least the log of that. In fact, at least this much. And why is that? Because if you can do something with interaction, you can always simulate it by a one-way protocol by just imagining what the other person would respond. So it's exponential. So this is sufficient to solve the leak problem, because we saw that we had a protocol with 2 messages that required at least log n plus 1. But 2 messages is bigger than L infinity. And L infinity by this is at least log L plus 1 and log S plus 1. And log L and L1 was log n, so you get log n plus 1. All of these must hold with equality. Okay? So that means that 1 message can be exponentially wasteful. So for example, for the leak case, L1 is 2 to the L infinity minus 1. This was log n, this was log n. It's exponentially, if you insist on a single message, you require exponentially more bits you might require. There's some problems for which this is true. Okay. However, and one of the interesting results here says that 2 messages are almost optimal. If you allow 2 messages, you're almost always at most 4 times away from the optimal. So there's no pointer jumping or pointer chasing or any pointer stuff that you can be arbitrarily off after 2 messages, so you're within a factor of 4 for all these problems, all communication problems. You can also show that 2 messages are not optimal. There are problems such that with 2 messages you're twice away from the best. And you can also show that for most sparse means there are not too many, the support set is not too dense. Most sparse distribution, the recipient actually must transmit most of the bits. A little counterintuitive, just like in the league problem. The person who wants to say something transmits few bits. The person who wants to hear says most of the bits. So what are the open problems here? So first question is, how large can L2 be? So we just said that L2 is always 4 times L infinity and can be twice. Can this gap be closed? Problem 1. And then maybe a more interesting question is whether there's a fixed number m, maybe 3 or 4 messages, such that m messages are asymptotically optimal for any problem. So that's an open problem.
So when you write general distributions, you've been talking about worst case. So what do you mean there? Do you mean?
No, that's a very good question, because right after this slide, I'm going to go to non-general distributions, but you will not see that. So, yeah. So these are questions that apply for all distributions. Next slide, I'm going to talk about like distance distributions. They have more structure.
Is the role of distribution just this support set?
Second, please.
Distribution is just its support set.
Correct, because we are.
Care about the weights.
Correct. Because we're asking about worst case, then the only thing you care about is the support set. If you asked about the expected number of bits, you'd care about the actual distribution. Absolutely.
So the statement at the bottom, that's a theorem? Or
Yeah, everything here is a theorem. Everything. No, it's not a folk, even not even a folk theorem, it's a theorem.
What do you mean by for any problem?
So if you give me any set S, you come up with any scenario that you have in mind. This is X, this is Y, these are the possible connections between them, these are the possible X and Ys that are possible. Whatever you can do with any number of messages, with 2 messages, you can do at most 4 times that much.
So basically any problem is a graph?
You can view it from either as a graph or as a subset of the Cartesian product. That's the more natural way. But it's also, you can view it as a graph, that's correct.
So I can't get the problem out of my head. How do you do pointer jumping in 2 messages?
No. This is not, okay, so I think I have a slide that relates this to communication complexity. This is not a general communication complexity, one, because this is not a general function. Here, f of x and y is x. I just want to communicate to you my value. So pointer jumping, the function is more complicated than that. So I have a slide about this, but in communication complexity, the set of possible inputs is trivial. Every x and y are possible. The interesting part comes from the function. Here it's the opposite. The function is trivial. F of x and y is x. The interesting part comes from the support set.
So I know an edge and you know one of the vertices and you need to tell me that vertex. So
I would like to think of it as a Cartesian product. You know a row, and I know a column, but not every row and column are possible. So that has a direct, maybe I have even a slide showing.
Graphs, each one knows one vertex, and there's a graph, and each person knows the input is an edge. Each person knows one vertex, and they want to know the other person's vertex.
I'm not sure that it's exactly the same, because if you said hyper edge, yes. If you're talking hyper edge, yes. But if you're talking edges of a graph, it's not always the case. Maybe I have. Let me see. I think I have something that. Okay, just one second. Okay, so here's the difference between this and communication complexity. Then we'll answer both of you. Okay, so communication complexity, I don't need to tell anyone here, but you have x and y, everything is possible, and the interesting part comes from f, as we said. Okay, and you ask how many bits need to be exchanged. Everything is the same. It's just that everything is possible, but there's an f inside. And here you know this is at least as of like many years ago the pointer jumping chasing problem. So there could be an exponential gap between any m and m plus 1. In this case, it's a different problem. So this was defined with Abbas El-Gamal many years ago. And you have x and y, and there's some subset that we both know of possible values. Okay, so if you want to look at it as a graph, like I think you guys are looking, then what happens is that you can look at these as the vertices of the graph, and these are the hyper edges. So I know a hyper edge, and I know that you are in one of the vertices. So you need to say hypergraph.
Well, you can also model it as a graph.
No, Yeah, if you want bipartite, then you could do that, but then it's not one has a vertex and the other one has an edge. Both of them has a vertex and they're connected. Yeah, so there are three valid ways of equivalent ways of looking at it. Okay, so here we're talking f of x and y is just trivial x, and you can see that in this case, two messages are asymptotically optimal. So now I want to go to the non-general case, like a subset of these problems, correlated files. So this whole problem is motivated by the following somewhat special case, which is you have two people and each of them has a file and two files are closely correlated. Okay. Why? Maybe the successive image frames, so you transmit images one after the other. The receiver has the previous image, you have the new image, and you want to communicate the new one. So the two, what the receiver and what the sender has are closely related. Or you have downloaded the previous version of Yosemite, and now you want to download the new one. The two files are somewhat related. Or if you're in the cloud, you have distributed database, and the files are fairly similar in two different locations. You want to synchronize them. Okay. So in all those cases, you cooperate in order to convey the file, and you ask how many bits you must transmit. It's a special case of this one. Right. So in some sense that I will not describe, but it's fairly accurate, it suffices to consider the following simple problem. So imagine, which is finding one-way protocol for insertions. So what is the problem? So imagine that each of us has roughly n bits, and there are t in insertions, and n and t are known in advance. So the receiver knows a sequence of length n, y, and the sender knows a sequence of length n plus t, because it was derived from y by t insertions. And the two sequences are such that x can be obtained from y by t insertions. Okay. For example, n is 6 and t is 2. The receiver has this 6-bit sequence, and the sender has a sequence of length 8, which is obtained by two insertions, in this case 0 here and 1 here. Okay. If you can solve this problem one way, you can solve essentially a good chunk of the communication problems just by solving this particular problem. Okay. So the question is, how many bits must the sender transmit in order to convey his value? All right. So why are we looking at insertions? So there are two possible answers to this. First is the more interesting one, maybe why is this sufficient for almost everything? But I'm not going to talk about that. I just want to tell you why I'm looking at insertions as opposed to insert one and delete one or delete something. So if this is the sequence y, or that the receiver has, of length, in this case of length 3, if you look at it, the number of subsequences that the sender can have, if you delete one bit, it depends on the sequence that you start with. If you start with the all 0 sequence, there can only be only one sequence. If you start with 0, 1, 0, then the sender can have 3 different sequences by deleting one. So we don't like that. If you look at insertions, then it doesn't matter what the receiver has y, the sender will have the same number of messages. In this case, 5. If you believe that statement, then it's easy to see that it's, look at the all 0, then how many will have? You can have the all 0 sequence and then inserting 1. So it's going to be, in general, it's going to be n plus 1 plus 1. N plus 1 chooses 0 plus n plus 1 chooses 1, which is n plus 2, in this case 5. Okay. So there is a benchmark. If the sender, remember the sender knows the sequence, knew what the receiver had, if they knew, then they would just need to enumerate all these and say I'm the smallest one, the second smallest, up to the largest. They would need to transmit log of n plus 2 bits. You agree? So they would know what this person has. They would just pretend they're him. They'll create all possible super sequences. They'll tell them I have the first, the largest, or lexicographic, the second largest, and so on. So they would need exactly log of n plus 2 ceiling. Exactly. But in our problem, they don't know. The sender does not know what the receiver has. And the question is, can we approach this benchmark, this ideal number that you could get if you knew what the receiver has? And the answer is that for one insertion, you can. So maybe we don't have time to go over this. Is this clock correct, or did someone just move it up? Okay. Okay, so for one, you can get exactly what you need. And the open question is, what can you do for 2 insertions? I can just tell you that what is easy to show is that for 2 insertion you need between 2 log n, which is what you'd need if you knew what the other person has, and twice as much is easy to show. A little less difficult to show is that if you allow 3 messages, then you can get to the right number. 3 messages going once and returning once, you can get to the right number up to a logarithmic additive number. And the question is whether there's a one-way protocol that achieves, say, the upper bound or so on. Okay. All right. Okay. Second topic, information complexity. I'll pretend I didn't see. Maybe we can skip over a lot of stuff here because we heard a lot about it. So in brief, communication complexity problem is beautiful, but it's very complex. There is, you can look at worst case, expected case, randomized, so on. It's messy. But there's a nice concept that relates all these things, and it's the information complexity of the function f that was described by a paper by Amit here, and she, and with, and the, and dl. Okay, and what it is, it's defined in the words of Gilad. It's a creature which consists of mutual informations and a minimize over all conditional mutual informations, minimize over all protocols. And the nice things about it is that it's additive. If you take the function, raise it, look at multiple copies, it just multiplies, and it lower bounds all communication measures that you want. Okay. In particular, it also lower bounds the amortized communication complexity, which is just you repeat the function many times, and you ask how many bits do you need per instance. And so there have been a lot of works about these 2 problems, and about 4 years ago, so Braverman and Rao showed that, in fact, not only the information complexity doesn't just lower bound the amortized complexity, but in fact it's equal to that. So I just want to tell you about the information theoretic view of this. So in information theory, there's also been work on this, and the same, it's roughly 95, so celebrating 20 years. So the same definition of the information complexity was defined in this particular case for a given number of rounds. So the information complexity for 1 round, 2 rounds, and so on, and for the same reasons, and the same results were derived. So this is for 2 rounds. So it was shown that if you look at the amortized communication complexity with 1 round or 2 rounds, it's the same as the information complexity for 1 round and 2 rounds. And there were, in fact, these results are a little stronger because the upper bound. So if I'm not mistaken, you guys can tell me, in the communication in the computer science literature, the upper bounds are for bit error. That's correct. Like the error for every bit is less than epsilon.
If you start with IC with epsilon.
But here in information theory, you can actually get diminishing block error. So it's not just that every bit will have probability 1% of being wrong. You can have that the whole block, no matter how big it is, will have probability of 1% or 10 to the minus 4 being wrong. And in fact, most of the work in the proof is proving this part. And the lower bound is also for average error rather than per bit, which is also stronger. Just say that if you want the average error to be small, then you need that many bits. Okay. And so there were extensions. So these results were for 1 and 2, but there were also extensions for any number of rounds and so on. And just want to mention a couple of things that you get from looking at in the information. So I'm trying to advocate looking at the information theory literature a little bit, and also maybe gaining some intuition and some and seeing what's out there. So, so a couple of things that you get from looking at the information theoretic view is that you get diminishing block error probability, which at least in, we view this as the called sort of the gold standard, because you have a laptop with terabytes of data. You don't want 1% of the bits to be wrong. You want the whole thing to be correct. You can also get a communication region, namely not just the sum of the number of bits, but you can get like any which pairs are possible. The senders, one person transmits so much, one person transmits so much. This whole thing falls in the realm of rate distortion. And once you get to rate distortion, it's actually like a whole world. So you cannot just look at errors, like what people have looked before, but you can look at any, you can define what the error means. Like you can say that if the value, let's say the function takes 10 values, and the actual value is 6, and you got 5, that's a small error. But if you got 4, it's a larger error. So you can just look at the sum. Any measure between the actual value and the value that you're estimating, you can get a formula for. Yes.
So you know how to prove that with diminishing block error, the amortized communication complexity is equal to the information complexity?
Right. Not for these, but for the original one, just the error. You say, is there an error or is there not an error?
With the arbitrary number of rounds, with no restriction to the rounds.
Okay, I can tell you for sure that you can do 1 and 2 because I was involved in those results. The results, the extension is actually seems fairly, at least for some things. So okay, so these are the extensions that are by Ishwar and Ma. Okay, they showed the same thing for every R. When you look at the formula, it's not that surprising that it will generalize. And they also looked at what happens in the infinite case, like I think you guys looked at. I'm not 100% sure that they're looking at the block, but at least for fixed number of rounds, they should be able to. But in the infinite number of rounds, I'm not sure. They also had, so both we and they, this was just a tool for us. We were trying to get like some nice formulas that if you give me a function, there's a nice formula. So for example, for us, we related it to the graph entropy should be written here someplace. Conditional graph entropy. So for one way, it's conditional graph entropy, and they have a method for the general case, which they call alternating concavication or something, where they don't just want to look at this formula, but they want to tell you what the answer should look like. But I don't know if those are for the block error. For ours, it's our block error. Okay. So yeah. So once you have this, you can look at any kind of measure that you have between the correct value and the incorrect value and the x and y. You can have a formula for that. And also, once you get to rate distortion, all this thing is a question of minimizing mutual information. And there's a formula, there's an algorithm called the Arimoto-Blairhout algorithm. So you can there's actually even like a MATLAB routine that you can plug in. So it's not exactly for this problem, but you can probably adapt this algorithm and get something that will approximate what you want. Because it's just meant for this problem. You have a rate distortion problem, it's a mutual information, you want to minimize it, just like in this case. And it's a way to solve it. You do it iteratively because you have x and y, and you iteratively go between x and y. I think, okay, so there's the third topic, which I can tell you if you want later on. Yes?
So they seem very similar to Slepian-Wolf and Wiener-Ziev settings. Is this connection clearly worked out, or is this?
Yeah, definitely. So the case where f of x, so remember if you go back to the previous case, f of x and y was x, that is the Slepian-Wolf case. But here it's a function that you want to learn, so it's more complicated than Slepian-Wolf, but it's related to Wiener-Ziev and many of the results you get from that.
I guess in the interactive case, it's not quite clear it's exactly the Slepian-Wolf, right? The L equal to 1 case is identical to Slepian-Wolf. But the L equal to 2 case almost seems like you need an auxiliary random variable or something more than just.
Okay, so you're talking about f of x. F of x is x. Perfect. Excellent. So what we saw is that if you have a single instance, you need to interact. Like in the leak problem, you need to interact. If you took this instance and repeated it many times independently, like what everyone is doing when they talk about interactive communication, they have X and Y, some distribution, repeat it many, many times independently. If you do that, you're in the Slepian-Wolf realm. And then you know that h of x and y is the minimum that you need to get, that you can get by with, and Slepian-Wolf will give it to you. So if you repeat it many times, there's no need for interaction. In the one case, yes, but when you
It's not clear what you do on the
just repeat twice.
No,
You,
but you're allowed 2 rounds.
but if you take your problem and you duplicate it many times independently, you will not want to do 2 rounds.